All right, so we're doing our recitation, and we're continuing our look at multiple integrals and several part integration. I want to start off by looking at this principle of symmetry and using geometry to try to figure out what some of these integrals look like. So I'm going to start off with a couple examples of those. So as our first problem, first thing we'll look at. So you want to take the double integral over d of this function, r squared minus x squared minus y squared dA, where d is the disk with center, it's a disk that's centered at the origin, and a radius of r. So as always, the first thing we should try to do is draw what this thing looks like. So in this case, the figure is pretty simple. It's just a circle, or really specifically a disk, because the circle we have to assume is filled in, centered at the origin with a radius of r. So that's the scenario that we're working with. So how are we going to do this? Well, what we notice is that root r squared minus x squared minus y squared, what is that? Well, if z equals root r squared minus x squared minus y squared, what we notice, and the hint here is that, well, wait a second, a square root of a radius minus x squared minus y squared, that looks an awful lot like part of an equation for a sphere. So if we decide to square it, r squared minus x squared minus y squared, what does that give us? That's going to give us x squared plus y squared plus z squared equals r squared. And so now what we can conclude is, oh, wait a second, that's just the top half of this sphere. So let me give a slightly different figure. Basically what we're looking at now is something that looks like this. We're trying to figure out what this volume is. So here's our x, y, and z as before. And also, I didn't write this in, but those we have to assume are x and y. And we want to figure out what the volume of this thing is. And now it's a much simpler problem. Again, its radius is r, and it's centered at the origin. And because that's what the surface is, that's the surface, z equals root r squared minus x squared minus y squared. So that integral that we're interested in, this double integral over d of this whole thing, r squared minus x squared minus y squared dA, that's just the volume of this half sphere. Or in other words, 1/2 of the volume of a sphere, which is 4/3 pi times the radius cubed. Or in other words, 2/3 pi r cubed. And we didn't have to do polar coordinates. We didn't have to do any real integration. We just had to think a little bit about what the geometry of this thing actually looks like. That's the benefit of doing things using geometry and symmetry instead of having to do calculus. But that was a relatively straightforward example. Let's do a different one. What if we now want to consider the double integral over d of the function 2x plus 3y dA? In this case, d is going to be the rectangle of all x and y, so that x is between 0 and a, and y is between 0 and b. So what does that look like? Well, here's what we're going to do. What we have to think about is, well, that's obvious, that's just a rectangle. Now, the thing we have to keep in mind here is what's going on inside. Z equals 2x plus 3y. That's a plane. It's not just any plane. It's the plane that's given by negative, actually, I'll write it this way. It's the plane that's given by 2x plus 3y minus z is equal to 0. So the gist here is to use geometry to try to figure out what that looks like. So the way we're going to do this is we're going to write this integral as the double integral over d of the function 2x dA plus the double integral over d of the function 3y dA. And so with that in mind, we're going to recognize that, okay, wait a second, for 2x, let's think about that for a little bit. 2x, if z equals 2x, what that really means here is x and here's z, and here's the line, wait a second. So here's the line, z equals 2x. From, now a is going from, so x is going from 0 to a. So if we take that into 3 dimensions, what that's going to give us is this figure. You're going to get this, and again, you've got your x, y, and z coordinates. You've got your line segment that we had before. Again, this is, going down to a and to 2a. But it's above the square or the rectangle from a to b. So here's what this object looks like. It's this block, right? It's this half of the block. And I'll draw that one as well. So it's that half of the block. That's what the first thing is going to look like. And the volume of this object is 1/2 of the volume of this block, which in this case is a times b times 2a, or in other words, a squared b. And similarly for the 3y, I'm trying to make it a little more straight, a little more vertical. Geez, I can't draw today apparently. Let's say that we're working with z equals 3y. It's basically the same principle in this case. Here I'm going to say that that's 3y. It's not exactly I'll try to make it a little steeper so it's a little bit of an obvious difference here. Going from b to 3b in this case. And so once again, we're going to look at this in 3 dimensions and find that what this is going to become b 3b whoa, 1 second, sorry. So now this is the block that we're interested in. It's pretty much the same exact story as before. In this case, the volume is going to be 1/2 of that object, which in this case is a times b times 3b, or in other words, 3/2 a squared b. So the entire volume, so the sum of both of these things, it's just, not a squared b, I'm sorry, ab squared. So altogether, this is going to become, this is all going to become ab times a plus 3/2 b. And that would be the total this total integral in that case. And how did we work that out? We worked that out by considering the volume of each of these, the volume that's generated by each of these two pieces. Now, can you do this with the entire plane? Yeah, you can. It's a little trickier. Can you, now is this really advantageous over, over just doing the direct double integral? Not really, but at least in this case, but it's another example of just showing what the geometry is of these different things that we're talking about. So I just wanted to point that out as well. So what if we want to do something a little different though? And this one's a little more significant. Should have maybe led with this one. What if we have the double integral over d of the function 2 plus x squared y cubed minus y squared sine x dA. And d in this case is all x and y, so that the sum of the absolute values is less than or equal to 1. Now, we really do in this case want to figure out what d is. So to do that, let's say that we've got y is positive. That means that y is less than or equal to 1 minus absolute value of x. So if we're drawing in our region, y is less than 1 minus absolute value of x. Well, here's 1 minus absolute value of x. This is not to scale, but let's just assume that these are all 1s. So you're going to be occupying this triangle in that case, if y is positive. On the other hand, if y is negative, that means that y is going to be greater than or equal to absolute value of x minus 1. Right? Why is that? Because that would mean that we've got absolute value of x minus y, because y is negative in this case, and we're talking about absolute values, is less than or equal to 1. And then you just do the algebra. So what that tells us is that we're now working in this lower part. So we get this diamond. This is D. This is going to be our region D in this case. And automatically we see that it's nice and symmetric, so maybe we can use that to our advantage. So this integral can be rewritten as the double integral over this D of 2 dA plus the double integral over D of x squared y cubed dA plus the double integral over D of negative y squared sine x dA. Now, in this case, you really do want to use symmetry because, well, any way you do this, you're going to have to break this thing up into a couple different pieces, whether or not you do it directly as a type 1 or a type 2, and that's going to be a little bit computationally annoying. So in this case, we're going to break this up with symmetry. Now, this is 2 times the area of D plus the double integral over D of this function, x squared y cubed dA, plus the double integral over the function negative y squared sine x dA. Okay, so so now that we've done this, 2 times the area of D. Well, what's the area of D? We can see that the area of D, so each of these lengths is root 2. So the total area of D is just 2 times root 2 squared plus, blah, 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 plus all that other stuff. Well, okay, that's simple enough. That's just 2 times 2, or that's just 4. So now we're working with 4 plus all of this stuff. Again, dx squared y cubed dA plus double integral over d negative y squared sine x dA. Now let's consider this, this double integral of x squared y cubed dA. Now x squared is an even function, right? X squared is an even function, which means you don't really need all of d. You only need one part of it and multiply that by 2. So you can consider, let's give this a different name. Let's say that we're going to talk about this piece, just the right-hand side of it, and I'm going to call that d0. And that's just going to be the right-hand side of that thing. And having done that, I can say then that this is just 2 times the double integral over d0 of x squared y cubed dA, because x squared is even. And when I say x squared is even, what I mean is that if you take some value of x on one side of this region, it's going to be the same value as on the other side, because you're squaring it. And if you square it, it doesn't matter what happens if it's positive or negative. It's going to be the same thing on both sides. So that makes no difference whatsoever. You only really need to consider what's happening with 1/2 of it, and then just double it. So that's one way that we can take advantage of symmetry and geometry here to not have to break this up in a whole bunch of different pieces. It's going to be the same in both cases. But actually, the story is even better. And the reason the story is even better, let's see what happens here. What's going to happen here is, well, y cubed. So this is happening since x squared is even. But now, if we try to integrate, now again, these are supposed to be the, let me try, oh, that's not what I wanted to do. Let me try making this a little bit more obvious what's going on here. What's going on here is that, so we've got this side of it, and here's, once again, this is D, I erased my label. So what's going on here is y cubed is odd. And since y cubed is odd, if you take, one side, if you take, let's say that you try to find what one piece of the function is on this side, it's negative of what's going on over here. They're going to cancel each other out. Because since this piece over here is what we call antisymmetric, meaning it's because y is going to be negative on this side, but positive on this side, and the same value, these two halves are going to cancel each other out. So y is odd, and what that means is that both sides cancel. Make this a little more explicit. I can, I can say that. Actually, I'm not going to do that just because the notation is just going to get kind of muddy, so I'm going to ignore that. But the point is, this all goes to 0 because both of these sides are going to cancel. I will be more explicit. I'll say that this is. I'll say that this side up here, I'm going to call this this piece up here, I'm going to call D1, and this bottom piece, which I'm going to do in orange, I'm going to call this thing I'm going to call this thing D2. The point is, these are, I'm breaking up the, all its symmetry is doing is breaking it up into different pieces. So that what this comes down to is this is 2 times the double integral over D1 x squared y cubed dA, plus the double integral over d2, x cubed squared y cubed dA. But that's 2 times, and all of this times 2, which is 2 times double integral d1, x squared y cubed dA, minus that same thing because it's the same behavior as one side on the other, just one of them is negative. So it's minus d1 x squared y cubed dA. And that's what I mean when I say this whole thing goes to 0. So in other words, this is, so all of this is going to become 4 minus double integral over d y squared sine x dA, which again, since y squared is positive, y squared is even, but sine x is odd, you're going to flip over in the opposite direction now, so flip over along the y-axis instead of along the x-axis, and in this case, the two sides are going to cancel again. So once again, you've got that this side is going to be one thing with sine of x, and the other side is going to be the same exact thing, but negative. So those guys are going to cancel each other out as well. So this becomes 4 minus 0. In other words, just 4. Now, if you're not convinced of this, if this doesn't seem particularly convincing for you, then I encourage you to take another look at it and try doing it yourself. Try doing it longhand, just actually going through the calculations of breaking it up into different pieces. And what you'll find is, wait a second, it's not a difficult anti-differentiation, but we can make it easier by taking advantage, just by taking advantage of symmetries and things like that. So it's not difficult, but spend some time working on it, and the outcome will make itself clear. So I wanted to point out a couple symmetry problems like that as well. Okay, but I also want to talk about center of mass. So this is one of the other big things that we're looking at in our homework this week. So center of mass and mass. So this is coming out of section 15.4. Now, if you learn nothing from this section, the most important thing to keep in mind is just what exactly is an integral. We're trying to figure out what exactly an integral is. So the important thing to take away from this is that the mass, so actually let me say this again. Suppose that rho xy equals the mass density of some plate or lamina, which we denote by d. Now, with that in mind, we can also say things like, okay, so then the mass, the total mass, is going to be the double integral over d of the density. And if you think about what density is, this makes a lot of sense, because this is saying that this is the mass, the density, which is usually in terms of mass per area, times the tiny amount of area. So it's mass over area times area. That's going to give you mass. So that's basically what this integral is telling us. It's the total. That's why I call it the total amount of stuff in some region. And that could be volume if you're talking about some surface over something. You can talk about mass. It can also be electric charge, and which is a little more interesting because charge can be negative. Mass can't be negative, but charge can, and you can talk about the total charge of a charged plate, like an electric potential or something like that. And the center of mass, same principle. Usually we write this as x bar, y bar, where the coordinates are given by x bar is equal to 1 over m times the double integral over your lamina of x times rho xy dA And y bar is 1 over m times the double integral over d of y rho xy dA. So it's basically just a whole bunch of calculations, but it's not terrible to work out what they would be. So let's do an example of this. And let me pull out the example that I wanted to do. Let's say that D is a lamina. Oh, sorry, lamina. Enclosed by the curves y equals 0 and y equals cosine of x for x between negative pi over 2 and pi over 2. And our density function rho is just y. Once again, we want to draw this figure. So, and the problem, of course, is to find the mass and the center of mass. So the first thing I'm going to do is try drawing this thing to figure out what it looks like. In this case, we've got a cosine curve. Right, we've got some cosine curve which extends in those directions. Pi over 2. Oh, sorry. Negative pi over 2 here and here. And the curve y equals 0. So here's our lamina. That's the lamina that we're interested in. We notice it's symmetric over the y-axis. Maybe we might be able to use that to our advantage. We'll see. And so let's find out what this thing really is. So the double integral, so the mass, we're going to need to find the mass first. Even to find the center of mass, we need to find the mass first. So the mass is the double integral of the function y dA. Now y, we're just integrating y. So in this case, well, we can't really use x in this case because x, well, that's not gonna. There is no x term, and it's not symmetric over the y-axis. If it were, by the way, if hypothetically, and we don't have this, but hypothetically, if we had that this thing was closed if that were a region, both halves of that thing, then this integral would be 0 because y is, okay, that's obviously an odd function because that means that the top part is positive, the bottom part is negative. It's the same amount of positive and negative. They would cancel each other out, and we'd be working with a plate that has 0 mass, and that's ridiculous. But you also can't have negative mass, so none of that makes any sense. So we're going to ignore all of that scenario. I'm just pointing out what symmetry would imply if we had symmetry. We don't have symmetry for this thing, though, so we have to do this directly. X is going from negative pi over 2 to pi over 2. Y is going from 0 to cosine of x. Y dy dx. Integral from negative pi over 2 to pi over 2. 1/2 cosine squared x dx. Now again, you're going to want to use the trig identity in this case. Cosine squared of x is equal to 1/2 1 plus cosine of 2x. And we're going to use that to our advantage in this case. This becomes the integral from negative pi over 2 to pi over 2 of 1/4 1 plus cosine 2x dx. And you can break that up without too much difficulty. That's 1/4 of just pi over 2 plus pi over 2, plus 1/8 sine of 2x from negative pi over 2 to pi over 2. But that's going to be sine of pi and sine of negative pi, which is 0. So that whole thing is going to go to 0. And we're left with pi over 4. pi over 4, which is approximately around, I'm sorry, that's not center mass, just mass. I lied, pardon me. So that's the mass. What about the center of mass? Let's look at the x-coordinate. 1 over m, or in other words, 4 over pi, the double integral over d of, now the function's going to be xy dA. Only this time, since we're integrating x is even, excuse me, x is odd, not even, it's odd. So that means that on one side, x is going to be negative, but on the other side, x is going to be positive for x. Now, these negatives and positives are just for x in this case. But that means that one side is going, if you fix y, if y is a particular value, one side of x is going to be negative, the other side of x is going to be positive. If you're not convinced of this, this one's actually, we can do directly, and you'll see exactly what's going to happen. This is going to be the integral. We're going to flip the bounds of integration in a bit of a funny way, and you're going to think, why are we doing this? But trust me on this. This is going to be good news for us. Because basically, what this comes down to is, I'm sort of cheating a little bit, but this is going from 0 to 1 in the y direction. In the x direction, this is going from arc. Excuse me. That would be negative arc cosine of. Yeah, it would be negative arc cosine of y to arc cosine of y of the function xy. This is going in the opposite direction, dA. Or in other words, 4 over pi, integral from 0 to 1 of 1/2 arc cosine y squared minus arc cosine y squared times y dy. And I don't really care about arc cosine y at this point because they're going to cancel each other out. This whole thing comes out to 0. Now, if you think about that for a second, that actually makes a lot of sense because we're talking about a lamina whose mass density in terms of x is perfectly symmetric. It doesn't depend, the mass density doesn't depend on the x-coordinate, only on the y-coordinate. So up here in this area, it's going to be more massive than down here. But the mass in each of these two lobes is, that's just going to be exactly the same. So what we've concluded at this point is that our x-coordinate for the mass density is 0. And considering that the mass in terms of x is symmetric on either side in this case, that shouldn't be that surprising. What about y? Let's look at the y coordinate now. Y, 4 over pi, double integral over d. In this case, is going to be y squared dA. Now, unfortunately, we have to do this one directly as well. So, but it's not that bad. 4 over pi, integral from negative pi over 2 to pi over 2, integral from 0 to cosine x, 1/3 y cubed, I jumped the gun a little bit, y squared dA, which becomes 4 over 3 pi integral from negative pi over 2 to pi over 2 cosine cubed x dx. And cosine cubed is that's a little bit frustrating to deal with, but it's not not dreadful. You're basically going to have to use some kind of trig identity, and in this case, the trig identity we're going to use is quite clever. So here's what we're going to do. We're going to say this is 4 over 3 pi, integral from negative pi over 2 to pi over 2. The other trig identity you can, for cubes that's really good is, we can use, I don't really have much room to write this. I'm going to write it up here. Remember that cosine squared x is also equal to 1 minus sine squared x. And this identity over here that's very good for cubed trig functions. And the reason why this becomes cosine x times 1 minus sine squared x dx. And I'm running out of room, but I'll just do this on the I'll just finish this on the next page. So we're working with 4 over 3 pi integral negative pi over 2 to pi over 2 cosine x 1 minus sine squared x dx. That becomes 4/3, or sorry, 4 over 3 pi, I mean, integral from negative pi over 2 to pi over 2 cosine x dx minus 4 over 3 pi integral negative pi over 2 to pi over 2 cosine x times sine squared of x. And that's just a u sub. That you can do with a basic u sub, and that's going to become, and on the first side, we're going to get 4 over 3 pi times sine of pi over 2 minus sine of negative pi over 2, which is equal to 2, minus 4 over 9 pi sine cubed x from negative pi over 2 to pi over 2. Again, sine cubed of pi over 2 is 1, sine cubed of negative pi over 2 is 1, so this is also equal to 2. So the whole thing comes out to 8 over 3 pi minus 8 over 9 pi, which becomes, is going to become 16 over 9 pi. So the answer to all these questions, the mass is 3 pi over 4. Not 3 pi over 4, just pi over 4. Too far. The mass we said is pi over 4. And the center of mass, the x-coordinate, is 0. And the y-coordinate we just found to be 16 over 9 pi. So that's basically all of this that this stuff really comes down to, is just figuring out what these different formulas give us in terms of mass and center of mass and all that fun stuff. So I don't want to get too much into the volume stuff because I'd rather just do all that at once. So I'll stop here for now, and then tomorrow we'll look at volumes, and we'll look at volumes and other good stuff with other symmetry and do more fun problems. So we'll end here for today, and I will see you guys on tomorrow.